All right, the next type of function we're going to review are rational functions. Rational functions are ratios of polynomial functions. So it's natural to talk about them right after having finished talking about polynomial functions. And that word rational, you've seen before, right? So you may recall that the ratio of two integers is a rational number, right? In other words, fractions, right? Well, the ratio of two polynomials is a rational expression. So we're dealing with kind of fractions that involve x in them. To simplify a rational expression, we have to be able to factor out a common factor in the numerator and denominator. For example, if we were dealing with this function x squared minus 4 over x squared plus 4x plus 4, and we wanted to simplify it, one mistake that students often make is they start to cross off things like crazy, right? Like they want to cross off the x squares, they want to cross off the 4s, and it just doesn't work that way. What you can do is you can factor, right? The numerator is a difference of squares, so it goes to x plus 2, x minus 2. The denominator factors is x plus 2, x plus 2, and then the x plus 2's cancel, right? Once you've factored something out, you can cancel it off, and then you're left with whatever is whatever the remaining factors were. To clarify this concept further, consider these two statements, right? Here we have the statement x squared times x plus 3 over x squared times x plus 2. And in this case, because there's multiplication taking place between this factor and that factor, this factor and that factor, you can go ahead and cancel off the x squareds to get x plus 3 over x plus 2. When there's addition, though, instead of multiplication, you can't just cancel off the x squareds. It doesn't work that way. This is not the same thing as x plus 3 over x plus 2. This is the same thing as x plus 3 over x plus 2. This is not. And you can verify that pretty easily. Like if you're ever in a situation where you're like, I'm not sure if I can cancel this, plug in some numbers and see if it's true, you know? Like if you plug in, you could plug in almost anything you like and you'd see that this is not true. Like if you plug in -1, I suggest you plug in -1. If you plug in -1, you see that what you get on the left here is not the same thing as what you're going to get on the right. So, so these two expressions are not equal. If you want to simplify, the moral of the story is if you want to simplify a rational expression, you have to factor, and then you can cancel off common factors. But you can't just cancel off common terms, okay? So I'm going to walk you through some examples where we simplify some stuff, where we do some multiplication, some division. So let's get to it. So if I want to say, well, actually, go ahead and give the video a pause and see if you can try this one out on your own. Okay, here's my solution. Okay, so there's part A. I factored, and then I was able to cancel off a common factor. Part B, I think, is fairly similar to that. That's what you get on part B. It's there is a little detail here, which I think I'll talk about later on. But this statement is, well, it's mostly true. It's actually not entirely true. The way that it fails is because in this statement, or in this expression, right? This expression is undefined when x equals -2. Okay, so if x equals -2, then this expression is not defined. Whereas this expression is defined when x equals -2. So these two expressions are different. If you wanted to account for that, if you wanted to write down an expression here that's exactly equivalent to this one, then you'd have to say it's x cubed so long as x does not equal -2, right? And here you would say these two things are the same so long as x does not equal +3. Because when x equals +3, this thing is undefined. Anyway, That's just a little minor detail, which I think that we probably will talk about later on. Let's perform some operations, right? So multiplication works just the same way that it does for fraction multiplication. So you just multiply straight across, and then you can reduce by canceling off common factors. Or if you like, you could do the reducing before you multiply, right? By cross-canceling. Of course, here you have an additional step, though, that you first have to factor everything. So let's get to it. Okay. That will cancel that. That will cancel that. And that will cancel that. I think we're left with a 2 times x plus 1 over x minus 1. Okay, so there's that one. Division works the same way, more or less. You just have to remember to flip over the second fraction. In other words, I'm thinking of this middle fraction bar as a division problem, right? So I'm thinking this is x squared minus 2x minus 3 over 7x cubed plus 28x squared divided by 4x plus 4 over 2x to the fourth plus 8x cubed. Well, that division turns into multiplication, right? You multiply by the reciprocal of the second fraction. So I'm just going to do this all in one step. Times, and then I'm going to flip the bottom one over. And then you proceed just as you did in the previous problem, okay? Okay, so the x plus 4s are gone, the x plus 1s are gone. This x squared here will cancel 2 of these x's and leave one of them behind. And then this 2 and this 4 will cancel and leave a 2. Of course, I've got a 7, right? 7 times 2 is going to be 14. So if I throw it all together, I've got an x and an x minus 3 left in the numerator. In the denominator, I've got a 7, a 2. Oh, and that's it, right? Everything else got canceled. So that's what that one looks like. Okay. Addition and subtraction. We're going to do, so these two problems are addition and subtraction when you have the same numerator. And when you have the same, or sorry, when you have the same denominator. When you have the same denominator, that's not hard. Again, the addition and subtraction works exactly the same as it does for adding and subtracting fractions, right? If the denominator is the same, you just add the numerators and leave the denominators unchanged. So I'm going to add 5x plus 2x, 22 plus 20, divide by x squared minus 36. The only thing you should do is try to simplify if you can. So when you get to this step, you can factor. And then cancel common factors if there are any. So in this case, we end up with 7 times x, or 7 over x minus 6. Same thing in part D. Just be sure to be careful with the negative sign, right? So it's 4x minus 3x, and then 1 minus 4. And then let's see. I think this will be x plus 4 times x minus 3. The x minus 3's cancel. You're left with 1 over x plus 4. These things don't always reduce. Sometimes you get to this step and they can't be reduced, and that's fine. But anyway, that's that. Now, what happens though if you don't have a common denominator? Well, if you don't have a common denominator, then you need to get one, right? You need to force the denominators in the two expressions to be the same. So let's practice doing that. Let's find the least common denominator of each of these pairs of rational expressions. So the way I like to think about this is that I look at the two, and I'm allowed to add on any additional factors that I need to. I'm allowed to put anything I like here in the denominator as long as I put the same thing in the numerator. And I'm trying to get these two denominators to match. So if I go through this, it's like if I look at this one, I know that here I have an x squared and here I just have an x to the first power. So in order to get these two denominators to match, I'm going to need another x, right? I'm also going to need a 4 because I have a 4 here, but I don't have one there. So I'm going to need to put a 4 on. And I'm also missing 2 more x plus 2's, right? I have 1 copy of an x plus 2, but here I have 3 copies. So I need 2 more copies of the x plus 2 down in that denominator. So that's what I'm missing in order to kind of fill in the blanks there. So I'm thinking the LCD is going to be 4, right? 4 times x squared. And then I'm going to have the x minus 1 squared. And then the x plus 2 cubed, right? I can force both of these denominators to be this new denominator. Here I have to multiply by another x. I have to multiply by another couple x plus 2's. And I need to multiply by a 4, which I'm allowed to do as long as I also do a 4x times x plus 2 squared up there. And this one, I can get to match that by adding on not adding on, but multiplying on an x minus 1 squared. And then this looks just like that. The terms are not in the right order, but that's the idea. Okay, so there's the LCD of that first set. Second one's a little easier. What you have to do is you have to factor these things, but the denominators in part B are already factored. And they're already factored and they don't have any factors in common. So the LCD is just going to be the product of those two factors, right? And that's all there is to that, right? You force this one to be the LCD by multiplying by x minus 5. And you force this one to be the LCD by multiplying by x plus 2. And that's all there is to it. So in part C, I think we're going to have to do some factoring, right? We're going to say this is x minus 3 times x plus 2. This one is x minus 3 times x plus 3. And now if I'm thinking about what the LCD of this should be, here I'm missing an x plus 3. Here I'm missing an x plus 2. So I think the LCD is going to be x minus 3 times x plus 2 times x plus 3. Right? I can force them both to be this LCD. Okay, so that would be the LCD there. So that's how I think about getting the LCD. This shouldn't be the first time that you've been exposed to this sort of thinking. If it is and you need more clarification, you can send me an email or something and I'll walk you through it with a little more detail. Let's talk about this next one. All right, sorry for that brief pause there. I needed to, my daughter was in here asking me a question, but yeah, so let's do this next one. So let's subtract. Now, in order to subtract these two expressions, they have to have a common denominator. So the first step is going to be to force them to have the same denominator. In order to do that, I think the very first thing I'm going to do is factor, if I can. It looks like here I can factor out a 3. And then that's how that one factors, right? This is just x minus 5 squared. Here I can factor out a 2x, and I'm left with x minus 5. Okay, so it looks like I can force both of these numbers to be 6. In this one, I'm going to have to multiply by 2. Maybe let me use a different color. So for this one, I'm going to have to multiply by a 2 to get a 6, which means I need to multiply the numerator by 2. Here I'm going to have to multiply by 3 to get a 6, which means I need to multiply the numerator by 3. What else am I missing? Here I'm missing an x. And what else am I missing? Here I'm missing another x minus 5, right? So I've got to get another x minus 5 on there. But now if I work all this out, I'm going to have 6x times x minus 5 squared. And here I'm going to have 6x times x minus 5 squared. So I'm going to have the same denominator in both cases. So let's see what I've got. 2x times 2x is 4x squared over 6x times x minus 5 squared minus 18x times x minus 5 over 6x times x minus 5 squared. So that's looking much better, right? I at least have a common denominator now. I need to go ahead and distribute the 18x. Oh, what's that going to be? 40, so 90, I think. I better be sure. 18 times 5. Yeah, that's 90. Okay. And then I can combine my like terms, right? 4x squared minus 18x squared is going to be negative 14x squared. And then, you know, I guess you could say 0 minus negative 90 is a positive 90. I can simplify that a little, right? I can at least factor out a 2 and cancel it with the 2 down there. So I can say 2 times negative 7x squared plus 45 over 2 times 3x times x minus 5 squared. And then the 2's cancel, right? So my final answer, I think, would look something like negative 7x squared plus 45 over 3x times x minus 5 squared. And that's that. Okay, so that's how addition and subtraction are going to work. I'll give you an opportunity to practice a little bit. So go ahead and see if you can do part B on your own. Here's my solution. So here I think I'm missing an x minus 1. And here I think I'm missing an x plus 1 squared. So I need another x plus 1. Oh, that's not going to factor. That's not going to factor. So I think I'm done. Okay, so there's that one. And part C. Again, give the video a pause. See if you can work this out on your own. Okay, here's my solution. Okay, yeah. Negative x plus 2x is a positive x times 4. Four x minus 3, or 4x squared minus 3x squared. And this isn't going to factor, so that's as far as that one goes. Okay, so that's how adding and subtracting rational expressions work. So we've talked about how to simplify, multiply, divide, add, and subtract. Another thing we can do with rational expressions is sometimes we have rational expressions within rational expressions, within larger rational expressions. We call these things complex fractions. And the strategy for simplifying complex fractions is to multiply by the LCD of all of the fractions in the problem. So for example, all of the little fractions in the problem. So like I'm thinking of this, this, and this as my little fractions. Their denominators are 3x, 3, and 3x. So if I think about the LCD, it would be 3x in this case, because I can force all three of these denominators to be 3x. In fact, these two are already 3x. This one I can force to be 3x by just multiplying by x over x. But the way that, so once I know what the LCD is, to clear these fractions, I multiply through by the LCD. So I'm going to multiply by 3x in the numerator and 3x in the denominator. And I'm allowed to do that because if I multiply by 3x over 3x, I'm really just multiplying by 1, which doesn't change the expression. So when I distribute here, the 3x's cancel, I'm left with 5. When I distribute here, the 3's cancel, but that leaves me with an x. X times 1, right, which is x. And in the denominator, the 3x's cancel, and that leaves me with x squared minus 25. So that does the trick of clearing all of the little fractions within the larger fraction. Okay. At this point, all I have left to do is simplify if I can. I think I can in this case. I think x squared minus 25 will go down. I'm going to rewrite 5 plus x as x plus 5. And then x squared minus 25 is x plus 5 times x minus 5. Same thing on part B. I would look at all the little fractions, in this case, this one and this one. And the denominators are both x, so the LCD is easy, right? I'm just going to multiply through by x. When I do that, I get 2x. Here the x's cancel and leave just a 2 over x plus 2. So I could factor out a 2 from the numerator, but I don't think it's going to cancel with anything in the denominator. So I think that's as good as it's going to get. Okay. So we can simplify rational expressions now, right? We've talked about simplifying by adding, subtracting, multiplying, dividing, clearing complex fractions and stuff. Another thing that we want to be able to do is solve rational equations, right? So we want to be able to solve for x if we're dealing with an equation. Again, the strategy, Again, the strategy here requires us to figure out what the LCD is, and then we're going to multiply through by the LCD in order to clear the fractions. And then one thing that we have to do with rational equations that we didn't have to do with any of the equations we've seen so far is we have to check for extraneous solutions. Extraneous solutions are they're answers that you get when you follow the algorithm, but that aren't actually solutions to the equation. And in particular, what happens is sometimes when we multiply through by the LCD, we end up introducing extra solutions that come from the denominators. And the problem is that then if you go to plug those back in, they make the denominators 0. And if the denominators are 0, then actually the expressions involved in the equation are undefined, and so it's really nonsense. So we don't consider those to be true solutions to the equation. We kick them out of the solution set. So let me show you a couple examples of this in case you're a little rusty. So looking at these three denominators, 6, x plus 1, and x, they don't have any factors in common. So the LCD is just going to be the product of those three things, 6 times x plus 1 times x. So I'm going to go ahead and multiply through both sides of this equation by, and actually it's going to be each term. So I'm just going to do this term by term, right? I'm going to do 6 times x plus 1 times x. I'm thinking of that over 1 here. And then I'm going to do the same thing on the second term, 6 times x plus 1 times x. And then same thing over here, 6 times x plus 1 times x. So in the first term, the 6's cancel. We leave an x plus 1 times x times 1. In the second term, the x plus 1's cancel. They leave a 6x. And on the right-hand side, the x's cancel, and they leave 6 times x plus 1. And everything else, all of the denominators are cleared now, which is really pretty nice. So now we get x squared plus x plus 6x equals 6x plus 6. So x squared plus 7x equals 6x plus 6. Now to finish solving this, this is just a polynomial equation. So we solve it by moving everything over and then factoring if we can. So I move the 6x over, I get x squared plus x minus 6 equals 0. That does indeed factor. So I get x equals negative 3 or x equals positive 2. Now, to check to see if either of these are extraneous, what I need to do is plug them back into the original equation. And if they make any of the denominators 0, then they're extraneous solutions, okay? So if I plug in negative 3, here I get, well, 6. Here I get negative 2, and here I get negative 3. So none of the denominators there are 0, so that's fine, right? If I plug in 2, 6, 3, and 2, so 2 is also okay, all right? So both of these solutions are true solutions. They're not extraneous. Right, so there's my solution set. Okay. Here's another example. On this one, before we can even figure out what the LCD is, we're going to need to factor these denominators. So this one's going to be x minus 9 times x plus 1. This one's going to be, oh, what is this one going to be? 9 and 4, I think, will get us to 13, right? So I'm thinking x minus 9, x minus 4. Okay, so that tells me here I'm missing, well, I was about to try to get common denominators. I really don't need to do that. What I need to do is multiply through by the LCD. So I think the LCD is going to be x plus 1 times x minus 9 times x minus 4. minus 4, minus 4. Okay, x minus 9's cancel, x plus 1's cancel. I'm left with x minus 4 times x plus 3 on the left-hand side. On the right-hand side, x minus 9's cancel, x minus 4's cancel. I'm left with 6 times x plus 1 on the right-hand side. Now let's see what we get. X squared plus 3x minus 4x is negative x minus 12 equals 6x plus 6. Now since this is polynomial, move everything over. X squared minus 7x minus 18 equals 0. Then I try to factor that. I think it'll be negative 9 and positive 2. So x equals 9 or x equals negative 2. Now I need to plug these in to the original to see if they make any of the denominators 0. When I plug in 9, we get 9 minus 9 is 0, times 9 plus 1 is 10, 0 times 10 is 0. So it makes this denominator 0. It would also make this denominator 0. So x equals 9 can't be a solution. Because if it were, if we considered it a solution, we'd be getting something that said some undefined quantity is equal to some other undefined quantity, which is nonsensical, because if they're undefined, how can you say if they're equal, right? So 9 is not a solution. Negative 2, though, if I plug in negative 2, here I get negative 11, here I get negative 1, that's just 11, so that's fine. Negative 11, negative 6, so that's just positive 6, so that one's fine. So negative 2 works. So my solution set in this case would just be negative 2 and not 9. Moral of the story, check your solutions. Check them in the denominators of the original to see if they make any of the denominators 0. If they do, then you've got to reject them. Finally, let's talk about graphing these things. So graphs of rational functions you may or may not have seen in the past. Excuse me, sorry. But you may or may not have seen graphs of rational functions, although I think back in chapter 1 we did look at a rational function together. But if you refer back to 2.0, the introduction to this chapter, then you have that list of the functions and what they look like. And so you'll notice these two functions on that list. This is what 1 over x looks like, and this is what 1 over x squared looks like. The pieces of information that I need you to graph for these are the asymptotes. So first of all, they both have a vertical and a horizontal asymptote at 0. Vertical and horizontal asymptote at 0. And then the other thing that I need you to plot are, for 1 over x, I need you to plot the point 1, 1 and the point negative 1, negative 1. For 1 over x squared, I need you to plot 1, 1 and negative 1, 1. Okay. If you do that and you have the basic shape and you have the basic shapes of these graphs memorized, then you should be able to graph them. So now let me give you some examples. Sorry. Okay. Okay. So let's graph these functions, graph the asymptotes. We'll find the intercepts if they have any intercepts. Well, maybe. So let's do 1 over x plus 2. This is the same as the function 1 over x, but it's been shifted up 2 units. Okay. So instead of having vertical asymptote at 0 and a horizontal asymptote at 0, we're going to have a vertical asymptote. Our vertical asymptote is going to be shifted up 2 units. Well, so then it's still going to be a vertical asymptote at 0, right? Our horizontal asymptote is going to be shifted up 2 units. So instead of being a horizontal asymptote at 0, now it's a horizontal asymptote at 2. And now you can think of these asymptotes as our new axis system. So we need to plot, for 1 over x, we need to plot 1, 1 and negative 1, negative 1. and then just remember what the function looks like, right? So it kind of looks like this and this. Okay, and that's really it for part A, right? We've got the asymptotes on there. We've graphed the functions, or the function. It said to find the intercepts. Notice that we're not going to have any y-intercepts. There's an asymptote on the y-axis, so we know that these functions are not going to cross the y-axis. However, there is an x-intercept right here somewhere. So we can find that the same way that we find the x-intercept of any function. We plug in 0 for y, and then solve for x. So I'm going to move the 2 over, multiply both sides by x, and then divide by the -2. So the x-intercept is the point -1/2, 0. So I guess I didn't draw this super well. It should have crossed the x-axis at -1/2, right? But that's that. Now contrast that with part B, which looks really similar. Part A was 1 over x plus 2, and part B is 1 over x plus 2, right? But the difference is that here, this shifted the function up 2 units. This is going to shift the function left 2 units. So now I'm going to have a vertical asymptote. Instead of having one at 0, it's going to be over here at -2. And the horizontal asymptote, instead of being at 0, it's going to get shifted left 2 units. Oh, well, so really it's still going to be at 0, right? And now this is my new axis system. Again, I've got the point 1, 1, -1, -1, and that's what my function looks like, more or less. This time I have no x-intercept, right? This graph is never going to cross the x-axis, but I do have a y-intercept, and I find that by plugging in 0, right, for x. All right, so 0, 1/2 is the y-intercept. So that's that idea. I don't think I'm going to find the x and y intercepts anymore, just in the interest of time, because I think you have hopefully the idea behind finding intercepts. It's the same as finding the intercepts of any function, right? Let's do 1 over x plus 2 squared. So again, contrasting that with part B, 1 over x plus 2, now we've got 1 over x plus 2 squared. Well, it's going to do the same thing. It's going to take 1 over x squared, and it's going to shift it left 2 units. So we're going to have a vertical asymptote there. We're still going to have a horizontal asymptote at 0. But this time I have the point 1, 1 and -1, 1 on there. And the function looks like a mirror image across this asymptote. Kind of hard to do a super accurate job by hand, but that's what that function looks like. Okay, so let's do one maybe a little more complicated with a little bit more going on. This function is the 1 over x squared function, so it's going to look more or less like this, except it's going to be pointing downwards, right? Because that negative sign out in front. It's also going to be shifted right 3 units and up 1 unit. So my asymptotes are going to be at 3 and 1. So this is my new axis system. Now usually I would have the point 1, 1 and -1, 1, but because it's been flipped over, it's going to be 1, -1, -1, -1. Right? And so this is the graph that I get. Okay. So that's that one. Okay. So by the way, the limit as x approaches -2 here doesn't exist. The limit as x approaches -2 here is infinity, right? limit as x approaches 3 here is negative infinity. Limit as x approaches 0 here does not exist, right? If you remember about limits, let's practice some more with limits, algebraically. So the idea that we've discussed in the past with limits is that if you can plug in this value into this expression and get something that's well defined, then that is the limit. But if you get something where it's like something over 0, then you have to do a little bit more work, right? And algebraically, what we can do is we can just simplify the expression and hopefully cancel off whatever is making the denominator 0. Okay, so let me give you this example. If we plug in 3 in the way that it's written now, so if we plug in 3 times 3 is 9, times 3 is 27, we get 27 minus 27 over 27 minus, well, 9 times 3 is 27, plus 12 minus 12, we get 0 over 0, right? Undefined. But actually, that's a good sign. Whenever you have 0 over 0, that tells you, when you get 0 over 0, that tells you that you can simplify, you can cancel off a common factor, and so hopefully doing so will allow you to plug in 3 later on. Okay, if you got something like 1 over 0, then that would be hopeless, right? For that, you would just have to make a table of values or something. But if you have 0 over 0, well, you can just try to simplify this. Now, x cubed minus 27, that's the difference of cubes, right? Remember, 27 is 3 cubed, not 3 cubed. So x minus 27 is the difference of cubes. So this is limit as x approaches 3 of x, 3, x squared, 3x, 9, right? I'm using my difference of cubes formula, and the signs are going to follow. So same, opposite, always positive. As for the denominator, I'm going to try to factor that by grouping since there are 4 terms. I can take out an x squared from the first group, and I'm left with x minus 3. From the second group, I can take out a 4, and sure enough, I'm left with x minus 3, which is nice. And look at that, right? When you plug in 3, that's where your issue is coming up, and it just so happens to cancel, right? So this is limit as x approaches 3 of x squared plus 3x plus 9 over x squared plus 4. And let's see now, if I plug in 3, I'm going to get 9 plus 9 plus 9 over 9 plus 4. It's definitely not 0 in the denominator, so that should work out. 9 plus 9 plus 9 over 9 plus 4. That's 27 over 13. That's the limit. Okay, so that's how we deal with limits of rational expressions. Okay, if they give us a 0, we start off by trying to plug in the number. If we get a 0 in the denominator, then we try to factor everything and cancel off a common factor. Then we try plugging in the number again. And as long as the denominator is not 0, what you get when you plug those numbers in is the limit of the expression. So that's that. One last problem. This is a really long section. I apologize. Thank you for hanging in there if you made it to this point. Let's practice calculating a derivative of a rational function. Ooh, this will be a good one. So f prime of x. It's the limit as h approaches 0 of f of x plus h minus f of x over h. So that's the limit as h approaches 0 of 1 over x plus h minus 5. There's f of x plus h minus 1 over x minus 5, right? There's f of x. So this is f of x. Sorry, this is f of x plus h. This is f of x. And we need to divide by h. Now, if we plug in 0 right now, we're going to get a 0 in the denominator, and that's not allowed, right? So we've got to try to simplify some stuff, see if we can cancel that 0 in the denominator. What's the best way to do this? I think probably the best thing to do would be to try to get a common denominator and combine these two expressions. The other thing we could do would be to just multiply numerator and denominator of the big fraction by the LCD, which is this times that. But I think the math is probably just a little easier to work out if I just do this. And do x minus 5, sorry, x minus 5 there. And x plus h minus 5, x plus h minus 5 down here. And let's see what we get. So these are common denominators now. I can just subtract these things. X minus x, the x's cancel. Negative 5 minus negative 5, so the negative 5's cancel. I'm just left with the negative h, right? So I have negative h over x minus 5 times x plus h minus 5 all over h. Now, I'm going to treat this large fraction bar like a division sign. So this is really equal to limit as h approaches 0 of negative h over x minus 5 times x plus h minus 5 divided by h over 1, right? So it's divided by h over 1. Well, that's the same thing as multiplying by the reciprocal. Okay, and now look at that. Those h's will cancel. So now if I plug in 0, I don't get, if I plug in 0 for h, I don't get 0 in the denominator. I get x minus 5 times x minus 5, right? Or in other words, x minus 5 squared. So there's the derivative, right? F prime of x is negative 1 over x minus 5 squared. Okay, so that will do it for this section.